can also make, okay, if all the informations are provided. Okay, so it's not that all the time the circuits will be drawn. That is how actually it happens in electronics. Okay, but then when you write down an answer, it is expected that you actually draw some kind of equivalent circuit, and based on that you do a bit of analysis, right? So the question says that you basically have a common base connection. So common base connection means that the base is common to both input and output, and you do get a lot of question where actually they are talking mostly about common base connection. Okay, and then the alpha, that's the current amplification factor, if you remember. Okay, so what we know here is the current amplification factor. So we have got okay, so we have got the current amplification factor alpha as IC by I. If you remember, yesterday we did it. Okay, alpha is equal to IC divided by IE. Okay, so we'll just look into this, and then we have got the voltage drop across the 2 kilo ohm resistance. Okay, just give me a moment. Alpha is equal to IC divided by IE. Okay, and the voltage drop is given to be around 2 volt. Okay, so the voltage drop is given to be 2 volt around the 2 kilo ohm resistance. So this 2 volt here. Okay, so that's the voltage drop across the load resistance that is connected across the output terminal. Okay, so this is the information that is given, and we also know that the emitter current, okay, is equal to the base current plus the collector current. Okay, so you should check it because all the formulas is already there on the screen, so we should all be able to do it, right? So the idea is very simple, that if you know the formula, you can basically just do it, right? So if you want to find out what is E, because here what you need is IE, okay, and you need what is IC, right? So both of these, if you know, then you can actually find out what is IB. And for that, what we do usually is this. What we do is find out IE first, okay? Or yeah, we can actually do it that way, or we can actually find out IC first. It will be more simple, okay? So just let's do it fast, right? So it's IC, the output is already there, and then the output IC is equal to nothing but 2 volt. Okay, that's voltage divided by the resistance. So this is this 2 volt, and then we have got the resistance, which is 2 kilo ohm, right? So this 2 kilo ohm. So if you just do this calculation, you are going to get just 1, and then this is kilo, so this will be 10 to the power 3 to go on top, so this will be 1 milliamps. Not you cannot get a very high current out of it. So when you do alpha is equal to IC is 1 milliamps, okay, amps divided by IE, then we can easily find out what is IE. Okay, so if we just calculate this, this will be 1 milliamps divided by alpha. Alpha is already given to be 0.95. Okay, this is for those who did not do, or it's not very clear. Okay, I think it's very simple. And if I do it, how much should I get? 1.05 milliamps. 1.05 milliamps. So you have this IE, and then you have got IC. You can just replace it here, and then when you get this will be IB is equal to IE minus IC. Okay. An interesting thing to note here is that yesterday I told you that there will be a very little difference between IE and IC. And how much is the difference can only be known if you know what is the value of alpha. Okay. So if you know alpha, you can actually see that IE will be 1.05 milliamps and IC would be 1 milliamp. So they're very close to each other. Okay, you can just take the difference and you should get the answer as 0.05 milliamperes. Okay, so I hope that this is not very complicated. Okay, it's simple. Let's go for one more sum. Okay, and then this is also something which I've made already ready. Should not be difficult for you. Okay. So whenever we are actually having any kind of circuit and you are actually earthing it at one part or the bottom, let's say I'm applying a voltage of 8 volt. Okay, so that means there is a potential difference of 8 volt between this and this. Okay, so if I earth this side, that means the potential at this side is 0 and then this side is 8. So in this way, if I draw a circuit like this, at the bottom everywhere there is earthing because there is no other component connected here. So sometimes we can even draw the circuit in this way. Okay, and then here we are given this. Okay, and the question is for the common base circuit. So we basically have the common base circuit here. Determine IC and VCB. So you have to determine what is this IC. Okay, this part is a question mark. Okay, And then what is VCB? So that means what is the voltage across this? This is the collector part, so this is the voltage here. VCB. Okay, so this is something which you have to find out. And this, a very important thing is this. It said that the transistor is made up of silicon. Okay, so that means the voltage across the base of the junction will be fixed, and that is nothing but 0.7 volt. So that is why this we have written this. Okay, so this silicon straight away tells me that voltage across base emitter is 0.7 volt. Okay, so you have to find out what is IC and VCB. Okay, and I'll give you a hint. Whenever you are having any kind of circuit, the Kirchhoff's law is valid for all the circuits. Okay, this is something which is more universal, the Kirchhoff's law, the Ohm's law. So we can actually use the Kirchhoff's law here. Okay, so what I'd like to tell you is just think about the answer and try to find it out. Okay, one more logic is here alpha is not given. Alpha is not given. Okay, so you really don't know how much would be the emitter current and how much different would be the collector current. So for all practical purposes, as I said yesterday, we can consider this emitter current to be almost equal to the collector current. See this? Okay, so that means if you find out the emitter current, you can easily say what will be the collector current. Okay, so on the collector side, we actually want to find out IC and we have got VCB. So there are two unknowns. And if you consider this particular loop, you can actually write down one equation here. So it becomes a bit complicated. But here, everything is known except IE. So you can use Kirchhoff's law, find out what is IE, and that will be nothing but equal to IC. Okay. So this is the hint. Use Kirchhoff's law here at this particular loop. Okay. Look into the voltage and the resistances and everything, and then put it into the equation. Okay. And then find out what is IE. Okay. VEE is equal to IE RE plus VBE. Okay, so you know what is VBE, you know what is VEE, it's already given. Okay, you know what is RE. Okay, it's already there. Just need to find out this is RE. Okay, we have it. So if you just use this formula, you are going to get your IE equal to 4.87 milliamps. Okay, which is equivalent to IC. So that's the answer. So once you have IC, you can actually write down the equation on this side also, and this should be very easy again. Okay, so you have got VCC is equal to ICRC plus VCB. Right? So you know what is VCC here? That's 18 volt, right? You know what is IC? Okay, this is the value. You already have it here. And then you know what is RC because this is 1.2 kilo ohm. Okay, so just find out what is VCB. This is the second part of the question. So just do it. Should get able to get VCB is equal to 12.16 volt. Okay, that's the answer. So all of you should actually do it individually. Okay, and one more suggestion I'd like to tell you, since we are doing it in a class, so I'm just explaining the steps and telling it to you, but in exam probably you should just write down some terms. Okay, some sentences at least. Okay, don't use much here. Probably you can just use applying Kirchhoff's law to, let's say, loop 1. You can just mark this as 1. Okay, and mark this as 2. Okay, or you can say that applying Kirchhoff's law to the input terminal and then applying Kirchhoff's law to the output terminal and so on. Anyway, you can write. Okay, just do it and I think that should be fine. Okay, so these are some sums, and we, as time goes on, every now and then we are probably going to talk more and more about these problems. Okay, so now what we are going to do is characteristics. Okay, so characteristics. Okay, let me just try out by using a pen here rather than typing. Config. So it's characteristics of common base configuration. So in whenever we are basically going to talk something like characteristics, it means that we are just going to plot a graph between voltage and current. Okay, so in the first part we are actually going to just write down the input characteristics. So number one, let's take it as input characteristics. Okay. So in input characteristic, what happens is whatever is the input current and divided by and the input voltage, we're going to plot a graph. Okay. So I think I can just plot it here, simple. Okay. So this is your current. Okay. On this side is current, and just let's say the unit is. Oh, sorry. Let's say the unit is milliamps. On this side, we'll actually plot the voltage. That's the emitter base voltage. Okay, we can just take it in volts. So just not changing the values that we might have, probable values. Okay, and then we'll basically have a curve something like this. Okay, and this input characteristics is observed at a constant collector base voltage. Okay, so let's say the collector base voltage is 0 volt. So if the collector base voltage is 0 volt, you're going to get this. And let me just write down some values here, maybe 0 0.5, 1, 0.5, and so on. Okay. So whenever you draw it for your exam also, and if you're explaining the input characteristics, I prefer that all of you please write down the values, okay, and don't be absurd in those values. Try to write down the values which are more practical and usually observed, okay. And generally, let's say this is 10 volt, this is 20, this is 30, and so on. Okay, so this is VCB, which is the collector base voltage, which is 0 volt. Okay, on the other hand, if we are actually having VCB to be higher, it may be that you basically have it on different. VCB is equal to 10 volt. Okay, so you'll be basically having, if the collector base junction is having a potential involved, you'll be basically going to have some kind of emitter current. Okay, so this is emitter base voltage, and this side is actually the emitter current. So maybe I can just write down IE, or I'll just write it down. I think it's okay. Emitter current. So this is what is the input characteristics should look like, okay? And there are certain points to note here. The very important point is that you see a slight change in voltage actually makes the current shoot up, okay? So that means slight change in voltage increases the current. That means the resistance should be more or less low, okay? So based on this, we can actually maybe we can write down a few points which might be important here, okay, to understand. Okay, so IE. Okay, I'll just write down IE, okay, and just consider this as to be the emitter current. You can just put it at the base, okay. E increases rapidly with a small change ECB. Okay, so V is EEB. Sorry, VEB. It shows that the resistance is small. We have the input characteristics, and the input characteristic we have got the resistance small because it is forward biased. Slight voltage, we can get to large current. Okay? And that is actually the fundamental theory of transistors also, which you might have already studied. Okay, so that's important. And you know that the emitter current is almost independent of the collector base. It is almost independent, you see. Okay, it's not really independent because what happens is there are minority charge carriers and all, which actually adds to it. Okay. One more thing that I think we should know is important is the input resistance. So how much is the resistance? I'm saying that the input resistance is low, but if you want to really measure it, how much do I measure? So input resistance. So if we just measure the input resistance, let's say, let me just mark it down as Ri. Okay, I'll just put it as Ri. Maybe I can just use the pen here, and then this will be Ri. So V is equal to IR. Okay, so R is equal to V by I. So we can just look into this, the change in the base emitter voltage, okay, divided by the change in current IE, emitter current. Okay, so if you do this, we are going to get the input resistance, and of course at constant VCB. Okay, So if you really want to find out what is the input resistance here, okay, we can basically consider 2 points, or we can actually draw a tangent, okay, and then we can actually drop a line here, we can drop a line here and find out what is the input resistance. So maybe we are going to find out what is the input resistance between these two regions, okay. We can just check this and check this, okay, and then we can take this current, we can take the current here, and if we have the graph like this, you can take delta VBE, so this will be, let's say, 30 minus 20, so you can put the value divided by IE, so you can just take whatever value is here and whatever value is here, and you take the ratio, whatever value you get, that will be in ohm, and that will be your input resistance. So that is important, okay. So now depends on, okay, the units, so it might not be ohm because it's milliamps at the bottom, so it will be in kilo ohm, okay. But then comparatively with output resistance, the input resistance, it is actually much smaller, okay. So that is input characteristics, and I think this is something which you already know. Let's just talk about output characteristics now, okay. So these electronic circuits and all, whenever you are purchasing any kind of digital equipment, I think I've already told you in case of Zenaders and all that, you will be getting some kind of data sheet, okay. So if you're buying a transistor, you'll be getting a data sheet, and that data sheet will actually have these images, okay, the input characteristic, the output characteristics, and as soon as you look into it, you straight away know that how good the transistor is, whether this will be actually useful for you or not, okay. So that is important. So here we actually have V, and this is, let me write down I. So in output characteristics, you know, whatever is the output voltage and whatever is the output current, I think this is very logical. So this is common base voltage, whatever you have, okay, and then we have got the collector current. This is also in milliamps, okay, and then we can just write down maybe 1 milliamp, 2 milliamp, 3 milliamp, and so on, okay. So this will be actually at a constant emitter current, okay. Now this will be at a constant emitter current, so this is important. And you know, whatever is the emitter current, you are going to get the same collector current, okay, approximately. This one something which we already know, and this emitter current will be approximately 0 milliamps. So as I said that if the emitter current is 0 milliamps, the collector current should also be 0 milliamps. So this is very close to 0, okay. This is not exactly 0 because yesterday we said something about leakage current, if you remember, okay. So then what happens is that if we are actually here, okay, I hope I'm just drawing it up to the scale. You can just draw it better than me, okay. Then maybe like this. If you understand the basic theory of transistors, this should not be very complicated to understand. This will be approximately 1 milliamps, okay, and then this would be 2 milliamps, okay, this would be 3 milliamps, and so on, okay. So you know, whatever is IE is approximately equal to IC, okay. But then if you just write down the exact value, this IC actually will be nothing but IE plus the I leakage current, LIL. If you remember leakage yesterday, I think I used this word, leakage current. So what happens is, even if the emitter terminal is closed, okay, it's open, sorry, no voltage is flowing. If the output terminal has some voltage, there are minority charge carriers which will actually add to the current, okay, and that is actually nothing but the leakage current. So this part is actually nothing but IL. It's a very small part, okay, it's a very small part. So for practical purposes, I think this is a good figure that we have. And you know, whenever you are actually going to have a collector current directly dependent on the emitter current, and since they will remain the same, hence this particular value will remain the same even if you increase the voltage, okay. You don't need to increase the voltage up to a point where the instrument get damaged, but it will actually have this saturation point, okay. Now the question is, why there is a point where from where it starts and then it becomes straight, okay. So this particular region where we have this small change is actually around 1 to 2 volts. So if the voltage is very low, okay, then what happens is there is some kind of thermal energy that is possible, because of which there might be some time that because if the voltage is low, the electrons needs to flow from this end to this end. So the electron needs to go from here to here, I. And why does the electron flow from this end to this end? Because we are applying a voltage at the output. So we are actually applying a reverse bias voltage VCB. Okay. So if it's a PNP transistor, you basically have a positive terminal here, and this positive terminal will actually attract the electron. Okay. But then if this voltage is very low, let's say 1 to 2 volts, you might not be getting much of electrons flowing, as a result of which the current will basically start from zero. And then slowly, as you keep on increasing the voltage, the current will keep on increasing, and then finally it will be almost equivalent to the emitter current. Okay, so the idea is simple. So what happens here is, usually during my time also I used to do it like this. Okay, I have to just remember the figure, and then from that, whatever analysis is needed, I have to just try to remember that. Okay, because if you remember, keep on remembering it and memorizing things, it becomes very difficult to remember electronics. Somehow, if you understand the basics, I think they should be okay. Okay. So I think we can just write down this. Okay, IC varies, since I said that, so I think important, with VCB. Okay, only at very low voltages. In bracket, I'll just put approximately 1 volt. Okay, so approx 1 volt. Okay, approx 1 volt. So that is the reason what I said. Okay, I think this is clear from this particular image. Okay, it should not be very complicated. Okay, this is the first point. And then what happens is, when the voltage is raised beyond this 1 to 2 volt, the collector current will become constant. Okay, so this straight line actually indicates that the collector current is constant, and it is almost equal to the emitter current. Okay, so if I ask you what analysis can you perform from the output characteristic graph, okay, I think this is something which you should explain. Okay, so at higher voltage, okay, IC is almost constant. I'll just put the almost constant because my slight variation. Okay, but I'll just put, since it is equal to the, or this is okay, this is, it is almost, because there will be the leakage current almost equal to the, or equal to. So when you write down in your exam, please make sure that you write down emitter current and collector current, and don't just write down IC and IE. Okay? One more thing, I think output resistance also we can just study here, and it's quite obvious. Output resistance, we can just know that, just write it down as RO. RO is equal to delta VCB divided by delta IC at constant IE. Now let's just look into this. VCB, it will vary here. Okay, 1 volt, 2 volt, 10 volt, 15 volt, whatever. So you can have some values here. But look at IC here. This is logical. IC, whether you take at this point or this point, the values are going to be very close to each other. There are going to be a minimum of variation. If you just zoom into the picture, then only you will see that this is there. Okay, so maybe I think I should use the word almost constant here, because if it is perfectly constant, okay, if it is perfectly constant, what happens? If this part is perfectly constant, if this is okay, let's take the pen. If this is perfectly constant, what happens is that at this particular point the value of IC, and at this particular point the value of IC will remain the same. So this will be a value subtracted from itself, so that will be 0. Okay, so if this delta IC, change in collector current, is 0, okay, that means RO will actually tend to infinity. So you're going to get an infinite resistance. Okay, so that means the output resistance is going to be very high. So for ideal transistor, it should be very high. Okay, for ideal transistors, it should be very high. Okay, so for ideal, basically it can be considered as almost infinity. But if there is slight variation, you will get some change, but this will be a very small value. So you are dividing a large value by a very small value, which is actually much less than 1. You're going to get a very high value of RC. Okay, so since delta IC is very small, you're going to get the resistance to be very high. So whenever, why this happens? Because the output is actually reverse biased. Okay, so whenever you make the main differentiation between the output characteristic and the input characteristics, you have to remember that the input characteristics, the resistance is low, okay, and output characteristic, the resistance is very high, okay, and whatever idea we had developed till now about transistor depicts this very clearly, okay. So please revise this part, okay, also this is very important, okay. So I think we can stop here today, and uh, this is the, you can say, the complete picture of the basics of transistor.